Another term that you need to know in the organic unit is this concept of homologous series. And all this means is that if I'm comparing alcohol A to alcohol B, but they're different molecules, that's still considered what we say a homologous series. You're comparing alcohols to alcohols. If I compare one carboxylic acid to another carboxylic acid of a different length or type or whatever, they're both carboxylic acids, so those would be considered a homologous series. If I'm comparing alkanes to alkanes, again, that's a homologous series. But if I compare alkanes to carboxylic acids or alkanes to alkenes, then those are not homologous series. All right, so we're going to look at boiling points here, and a lot of this information and how to determine or rank molecules with what their boiling points would be goes back to a lot of information that we learned in Chem 20 as it relates to intermolecular forces, things like London dispersion forces, dipole-dipole, and hydrogen bonding. If you want to go back and watch that video that I made on that subject, then you can do that as kind of a refresher. But it's not, I would say, completely necessary. It's nice to have it as sort of like a bit of a deeper understanding of the concept. But really what you need to know for this chemistry class is that boiling points are affected really by two things: whether a substance is polar or not, and how large the molecule is. So if we're looking at polarity, we have really kind of three types of molecules. We have molecules that can be very polar, we can have molecules that are slightly polar, and then we can have molecules that are not polar at all. And how that relates to boiling points is that molecules that are very polar are going to have very high boiling points, and molecules that are non-polar, very low boiling points. Now, for the organic derivatives that we've been talking about, we've mentioned four, and they are here listed right here: halides, alcohols, carboxylic acids, and esters. Those molecules can be polar molecules. Now, whether they're very polar or slightly polar will sometimes depend on their size. So here's an example of two different alcohols. This one right here would be considered very polar, and this one right here would be considered slightly polar. The difference between them, as you can tell, is the chain of carbons that's included in this second alcohol right here. Really, if you look at this molecule, it's a lot longer, and so this side kind of would be considered more of a non-polar side of the molecule, and this side with the hydroxyl group would be considered the polar end of the molecule. So altogether, we kind of just consider it to be sort of slightly polar. This one right here, though, a very small portion of the molecule looks to be non-polar compared to the side that's polar, and so if a greater portion of the molecule is polar, then we would consider it to be sort of in that very polar category. This one here obviously is non-polar simply because it doesn't contain any functional groups. It just has carbon and hydrogen bonds in it, and those are non-polar bonds, and so therefore it's a non-polar molecule. Another thing that you have to be aware of, though, when we're looking at polarity is a setup like this, where we've got the three molecules here that are halides. They contain the chlorine atom as its functional group. And this one right here would be considered very polar. And the reason why is, if you remember again from last year's chemistry class, these electrons are being pulled towards the chlorine. And because both of those chlorines are very much on the same side of the molecule, those electrons are being pulled in the same direction. And so it makes it fairly polar. These chlorines, though, there's a little bit of cancellation that's happening where we've got some of these electrons being pulled up, and these ones are kind of being pulled downwards at an angle. Now, because it's at an angle, there's still some polarity to it. It doesn't fully cancel out, but it's definitely not as strongly polar as this one. And then this guy right here, because the electrons are being pulled in exactly the opposite direction, then the polarity, the polar nature of that molecule is going to cancel out, and therefore this molecule ends up being completely nonpolar. So that concept you also need to know as it relates to what polarity a molecule has. The second thing that relates to boiling points is size, and this one's pretty simple. It's just a larger molecule is going to have a higher boiling point. A smaller one's going to have a lower boiling point. And that really comes down to the London dispersion forces that they have, that a larger molecule is going to have a total number of electrons that's going to be higher, and the number of electrons in a molecule is what dictates how strong the London dispersion force will be, therefore higher boiling point. So larger molecules, higher boiling point, smaller ones, lower boiling point. Fractional distillation is an application of boiling points that we've just been learning about. And so what exactly fractional distillation is that when we go out and we drill and we find oil, we take it to a refinery, and a refinery has these distillation towers. And this is really a very basic drawing of what's going on here, and a lot of the details of how these things are separated out isn't found in this drawing, obviously. But the main and basic concept that you need to understand for this concept of fractional distillation is when the oil is brought to the refinery, it's put in these big drums. And these drums are heated up to a really high pressure, or high temperature, about 400 degrees Celsius. And most of the substances in crude oil, this is a mixture, right? There's lots of substances that are mixed in that make up crude oil. They all have different boiling points because they're all different substances. They're going to be different sizes, or polarity is going to be different, or whatever. And so as these substances boil out at this really high temperature, what we do is we allow the vapors of that crude oil to now climb the tower. And substances that they're all going to have different boiling points. What we know is how high up the tower each of these substances are going to condense at. And so as these vapors make it up to, say, this first level, there's going to be a substance that's going to condense into a liquid at that height in the tower, because as it's moving away from the flame, then it's going to obviously get below its boiling point and condense down to a liquid. And when that happens, then we pull it out at that level. And that's the only substance that will get pulled out, because it's the only substance that would be a liquid at that height in the distillation tower. Then as the vapors continue to work their way up the tower, others will condense out and we'll pull them out at those various levels. And so these substances in this tower, a couple of trends you need to be aware of. The ones that have the highest boiling points are going to be the ones that are going to get pulled out lowest on the tower. And that's because as we move away from the flame, the substances are going to cool. So if I've got a substance in this crude oil that, say, condenses or forms into a liquid or boils, its boiling point is 390 degrees Celsius. Well, it's not going to be very long before it gets away from that flame that it's going to condense back down to a liquid. And so that's going to be the first one that'll condense out. The ones with the higher boiling points are typically going to be the ones that are the larger molecules. As we climb up the tower, at the very, very top, then the ones with the lowest boiling points are going to be the ones that are going to come out near the top. And those will be obviously basically mostly the smaller molecules in crude oil. So some examples, like butane is a fairly small molecule, it's only 4 carbons long. And then lubricating oils, somewhere between maybe 12 to 18 carbons long, would come out closer to the bottom. And then the last thing that you need to know is that there's a couple of substances that don't boil out, that have a boiling point of higher than 400 degrees Celsius, and that's tars and asphalts. And so all of these vapors kind of go up the tower, and then whatever's left behind is just tars and asphalts, and we use that to make roads and stuff as it relates to oil and those products that come from it. So that's what you need to know, guys, about fractional distillation and how things can be separated using this concept and our understanding of boiling points.